At this point, we have defined the underlying set and the topological structure of an affine scheme. Now we want to endow this affine scheme with a structure sheaf, because we need to define some notion of functions on any open subset of X. Remember that we are viewing elements of R as global functions on X, but as you remember already from the study of varieties, looking at globally defined things is not enough, especially not when later we will glue together our affine schemes into general schemes. So our goal is to define the structure sheaf, making X into a ringed space. The problem is that when we had varieties, everything was over a fixed field K, and so our regular functions were regular functions into this field K, and we have K algebras of functions and so on. But now, for each point, if we take an open set, so a set of prime ideals, and look at a point, meaning a prime ideal in this set, then we get the field kappa of P, that the residue field that varies with P. And even if we don't go all the way to this field, but look at rational functions, so things that are localized at the prime ideal P, this still also varies with P. So we need to take this into account. In the literature, as you can see if you examine, this can be done in two ways. The first way is to define concretely and thoroughly what local regular functions on any open set U are. So this should be U subset of X. The second way is to define regular functions on principal open sets and glue together. We will take the first road and then show that on principal open subsets we get the functions we expect. So what do we expect? We want what we had from the beginning, that the section of functions on principal open subsets, so sets where F doesn't vanish, this should be everything in R that doesn't vanish there, meaning the localization of R at F. Also, we want our space to be a locally ringed space. So we want the stalks of the sheaf at a point P. So this is the stalk at P in X, to be a local ring. And so a locally ringed space is precisely a ringed space such that the stalks are local rings. If you do not remember the definitions of stalks and sections and so on, I urge you to go back to the lecture on sheaves and refresh these concepts. Without further ado, let's get to the definition. So now we're looking at an open subset with respect to the Zariski topology of an affine scheme X equals spec R. So we want to define regular functions to be functions that can locally be written as quotients. So the precise way to say this is that a regular function phi on an open set U is a family phi p with one function for each point in U. This phi p should be in the localization of R at P. So the localization is where we invert everything that doesn't lie in P. So essentially phi p will be an expression of this form, G divided by F, where F and G are in R and F doesn't belong to P. But we want this not just at the point, we want this in an open neighborhood of P. So for any Q I should take this in the right order. We want there to exist functions F and G in R, so that for any Q in a neighborhood of P, this F doesn't belong in Q, and phi Q can be written as G divided by F. if you go back to the definition for varieties, this is exactly the same. If you sort of look at the special cases here, you want there to exist f and g so that your function locally around P can be written as g divided by f. And the set of all regular functions on U is denoted by Ox of U. And you can check as an exercise that this is in fact a sheaf of rings on X. So it should be clear that these form rings, and the fact that we have a local definition, meaning that we require something to be true in an open neighborhood, means that this will glue nicely, because then we can just take neighborhoods in the intersections of patches and get our sheaf condition. And this sheaf is called the structure sheaf of X, or the sheaf of regular functions on X. So these are the regular functions, and this definition is somehow the only reasonable way to make this into a sheaf. So let us look into some concrete realizations of this sheaf. So remember, we have a base of our topology consisting of these principal open subsets. These are the set of all P in X such that F does not belong to P. And since this is a base, it's enough if we understand the sheaf on the open subsets in this space, and indeed one can show that for any f in R, the section of the structure sheaf at the principal open set UF is the localization of R at F. The proof is by exhibiting an isomorphism that looks as follows. So any element in the localization RF is given as a quotient of g by f to the power r for some g in R. And you map it to the function phi that for all p in this principal open subset has the same look. It's g mod f to the power r as function. So this is straightforwardly checked to be a ring homomorphism, and injectivity also follows from the definition of Ox of U and of the localization. What is perhaps hard to believe is that this is surjective, because here this looks very rigid. I am choosing the same G and F for all of UF, and a priori I would need to shrink these to much smaller neighborhoods, but actually this is enough. The proof works as in the variety case, where you show that, if you shrink the neighborhood, you can assume that your shrunk neighborhood contains a principal open set, UH, and then you need to show that you can take this H to be in fact F, so you can work together with these notions to get surjectivity. I will leave the details out. As a corollary, you get that the section of global functions is indeed R. This is a corollary because X is U1 and the localization of R at 1 is just R. So believing the proposition, the corollary follows immediately. Then we have the locality. So the stalk U of X at P is isomorphic to the localization of R at the prime ideal P for any P in X. The way to prove this is to exhibit an isomorphism as follows. So remember, the stalk of a sheaf consists of the set of all pairs U open sets containing P and phi regular functions on these open sets modulo the equivalence relation that basically says that you consider two functions equal if they are equal at P. More precisely, you consider two such pairs equal if on an intersection the functions agree. Intersection containing P. And so such a class you map to phi of P. So remember, phi here is a family of phi P with P in U. This is quite involved, but if you sort of comb out all the technicalities, you get that mapping. So we need to choose some element in our P. Well, these phi P, each phi P belongs, so sorry, I shouldn't use P, the same letter, but say phi Q for Q in U, and phi Q belongs to R Q. And because of the equivalence relation, this will be well defined. So basically, the relation says that unless the phi P is different, the P part, so to speak, of this family, the P element is different, then these will all be the same. So this phi P contains all the information about this set. And I leave the details of the proof for you, being myself satisfied with that intuition. So now we have defined local functions or functions on open sets. So take a moment to look at these elements OX of U or OX of UF and think about what they mean. So if I have a function phi in OX of U and P in U, then I have phi P. So this is an element in Rp, the localization of R at P. And remember, I have R mod P, that is an integral domain with fraction field kappa of P. And so Rp, the localization at P, modulo the localization of the ideal P at P, this also has field of fractions kappa of P. So I can evaluate such a local function at the ideal P. This would mean the same as evaluating the global function. So remember, evaluating a global function f in R meant that I looked at the quotient as an element of kappa P. Now I do the same with the P element of my function phi. So there is a meaningful way to define phi of P, the value at P of a locally defined function. One warning, though, is that while in the case of an algebraically closed field, if I had a function phi, a regular function on U, then the function was determined by all its values. So if two functions were such that phi of P were the same for all P, then they were the same function. This is not generally the case anymore. As an example, let us look at the ring of polynomials modulo t squared, known as the ring of dual numbers over K, a field. If you want, you can take K algebraically closed. It works whichever you do. And so if I take X equals spec R, then what are the regular functions? So let's look even at the global regular functions. So OX of X, well, this is just R. So I can view this as functions of the, or polynomials of the form A plus B t, because anything t squared will be 0 with A and B in the field. Okay. So, but what is X? What are the prime ideals of this ring? Well, it turns out that in fact S consists of only one point, which is the ideal generated by T. And so if I take a global function f or phi in Ox of x, then phi of this ideal, this is the image of phi modulo T, so this is just A. This means that A plus bt and A plus b prime t have the same evaluation at every one of the single points in X. So X has very few points, but still I have multiple functions that give the same value. These are different elements of the ring R. The intuition behind this is somehow that when we dealt with varieties, eliminating nilpotents served to eliminate the case where we have too much freedom when we do not have that many points. But now we do have this freedom even when you don't have many points. So a variety with one point would have to be a field. And so, but now we are in a different situation, and therefore there are too few points for the functions to be determined by these points. This is also alerting to the fact that points of a scheme are not really the object you actually want to consider all the time. So keep this warning in mind. All right. So far we have defined what affine schemes are. An affine scheme is a set, the set of prime ideals of a ring, with the Zariski topology, where the closed sets are precisely the zero loci. And we defined the structure sheaf, which was defined in the way you expect and gave you the results that you would expect. So, in other words, an affine scheme is a locally ringed space of this form for some ring R. And locally ringed space, remember, meant that the stalks are local rings. Now, a scheme without the adjective affine is a locally ringed space, XOX, that has an open cover by affine schemes. So this simply means that locally ringed space means in particular that X is a topological space. So we know what it means for a set to be open, and we require this to be a union of UI such that each UI is spec of some Ri, and the restriction of the structure sheaf to the UI is the structure sheaf of spec Ri. Remember, for sheaves in general, in whichever context you deal with them, you have restriction. And so restricting to UI means simply that intuitively you look at only the regular functions at subsets of UI. This is a straightforward construction, and we require that the UI should be such that not only are they spectra of rings, but when you restrict the original structure sheaf of your scheme X, you get the structure sheaf of an affine scheme. So it is exactly what you would expect from this affine scheme. And so this is the definition of a scheme. It is very much akin to the definition of a variety in terms of affine varieties. Or is it? Well, It's actually the same as the definition of a pre-variety. So in the French school of algebraic geometry, these objects are not called scheme, they are called preschemes. And then in order for a prescheme to be a scheme in that sense, you require some separation. So remember, as we defined varieties from pre-varieties, you required that the variety be separated. But in the terminology and the literature we are looking at, and in most places I would say, you say a scheme for the analog of pre-variety and a separated scheme when you actually mean that you want the scheme to be separated. The second thing is that in this union of affine sets, there is no finiteness involved. So a scheme can be covered by an infinite number of open affine subsets without any possible finite cover. That thing is allowed. So now we have the basic definition of a scheme as a generalization of a pre-variety, and now we can work with these schemes in the coming lectures.